whatever byproduct you are getting here, again it is going to be used here, so that again dialkyl cadmium can be formed. Okay, so what is nucleophile again? Which is having attraction towards positively charged species, so it itself will be negatively charged, right? So the nucleophile, Nu minus we have mentioned here because it is a negatively charged species. So what you are going to get? Acetals. When aldehyde or ketone reacts with alcohols, you get acetals. Acetals are gem. What does this gem stands for? Geminal. Okay. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with session 3 of the chapter Aldehydes, Ketones and Carboxylic Acids. So in the last session we studied the nature of carbonyl compound, right? How the sigma and pi bonds are formed, as well as the preparation of aldehydes and ketones were discussed, right? And the preparation of aldehydes also in detail we have discussed, okay? First we studied the different methods using which we can prepare aldehydes as well as ketones. And we have studied the preparation of just aldehydes also. So in today's session, we are going to study the different methods of preparation of ketones, okay? Specifically, how you can prepare ketones, those methods we are going to study, as well as the physical and chemical properties of ketones. So beginning with the preparation of ketones, the first method is from acyl chloride. So we already know what is acyl chloride, right? And it is also called as acid chloride. That means from an acid, the OH group will be replaced by a chlorine. So that is called as an acyl chloride. So acyl chlorides are treated with dialkyl cadmium. R2CD is called as dialkyl cadmium. That means you have two alkyl groups and cadmium. CD stands for cadmium, which is obtained by the reaction of cadmium chloride with Grignard reagent. So how you are obtaining dialkyl cadmium? It is between the reaction of cadmium chloride, that is CdCl2, and RMgX, which is Grignard reagent, okay? And it will give you ketones, okay? So first let us see how dialkyl cadmium is prepared. So you have 2 moles of RMgX, that is your alkyl magnesium halide, which is Grignard reagent, reacts with CdCl2, cadmium chloride, to form R2CD. So you have these two R, okay, and cadmium will be replaced there, R2CD, and what is left behind? 2MgXCl, okay, you are going to obtain. So from this first step, this is your dialkyl cadmium. So now this dialkyl cadmium is going to react with acyl chloride or acid chloride to form the ketones. So as you can see, R-COCl is going to react with R2CD. What is going to happen here? Instead of the chlorine, what is going to happen? The R is going to be substituted here. So you're going to get R-COR you are going to get here, and the Cl which is going to be removed from here, that will combine with the cadmium and form cadmium chloride, which can be again used for the preparation of dialkyl cadmium. Clear? So whatever byproduct you are getting here, again it is going to be used here, so that again dialkyl cadmium can be formed, okay? So I hope this is clear. Let's take an example of ethyl magnesium bromide, CH3CH2MgBr. Again it's Grignard reagent, right? It is going to react with dialkyl cadmium. What you are going to get? Instead of the Br, you are going to get the alkyl group which you have taken, right? So we are using CH3 here. So let us take an example here of ethyl magnesium bromide. Okay, so this is the first step that is shown here. That is, the Grignard reagent reacts with cadmium chloride to form what? Dialkyl cadmium. So which is the alkyl group here? CH3CH2, that is ethyl. So what you are going to get? Diethyl cadmium you are going to get. That is CH3CH2 CdCH2CH3. Now this is going to further react with acid chloride and form the ketone, right? Now let's take another example of benzyl chloride, that is benzene group you have, on which you have COCl. This is benzyl chloride, right? To which again we are using ethyl cadmium, okay? That is dialkyl cadmium you are using. What is going to happen? This Cl is going to be replaced by your alkyl group, which is CH2CH3. That is ethyl will be replaced here, and CD and Cl will combine and form CdCl2. Clear? Moving on to the next one, from nitriles. So we already know what is nitrile. RC triple bond N is called as nitrile. While studying aldehydes also we have discussed this, right? So the treatment of nitrile with Grignard reagent followed by the hydrolysis gives a ketone. So nitrile can also react with Grignard reagent to form ketones, as well as acid chlorides can also react with Grignard reagent to form ketones. So nitriles, that is RC triple bond N reacts with RMgX, that is Grignard reagent. So this is mentioned as R dash to mention that it is both different alkyl groups that we have taken. So in presence of ether, what is going to happen here? So the nitrile RC triple bond N reacts with R dash MgX, which is Grignard reagent, to form a intermediate complex which on further hydrolysis will give you the ketone. So let us see, RC triple bond N stands for the nitrile which is going to react with R dash MgX, which is Grignard reagent. In presence of ether, what is going to happen here? The alkyl group is going to attach with the carbon because alkyl is partially negatively charged and MgX will have partial positive charge. Here also carbon will have the partial positive charge, nitrogen is going to have the partial negative charge because nitrogen is more electronegative. So what happens? MgX is going to attack the nitrogen and R will be attached to the carbon. So now what happens? If it is attaching, the triple bond will become a double bond, right? So that is what is mentioned here. This R is mentioned here. See the carbon atom you are having. Now to the nitrogen, MgX will be attached. So double bond N MgX will be there and the other alkyl group is going to attach with the carbon, which is shown here. Clear? Now it is going to undergo hydrolysis. We are going to add water. What is going to happen? This NMgX will be replaced by oxygen. We are going to hydrolyze it, right? And the alkyl group will remain as it is and this will remain. We are adding water, right? So you will have the OH also, which is going to combine with the magnesium and halogen, form MgOHX and ammonia will be liberated. So what you are going to see here, RCOR dash, what is it? It is a ketone, right? So now let's take another example of an ethyl nitrile. So that is CH3, CH2, C triple bond N reacts with phenyl magnesium bromide, that is C6H5Br in CH6H5 MgBr in presence of ether. Again, what is going to happen? The alkyl part is this one. So it is an aryl group actually, C6H5. So this is going to get attached to the carbon. MgBr part is going to attach with the nitrogen. So what you are having, CH3, CH2 and then to the carbon you will have the C6H5 which is shown here. And to the nitrogen you will have the MgBr. So nitrogen is already there and MgBr will get attached. Then it is going to undergo hydrolysis and what will happen? You will have the oxygen atom here. C6H5 will remain as it is and it will form again MgOH, Br and ammonia will be liberated. Again you got ketone. Clear? Now moving on to the next method, that is from Friedel-Crafts reaction. Okay, so by this time you are already familiar with what is Friedel-Crafts reaction, right? So when benzene or substituted benzene is treated with an acid chloride in the presence of anhydrous aluminium chloride. Okay, so we are using again acid chloride and in presence of anhydrous aluminium chloride, this reaction is going to take place. It gives the corresponding ketone. Okay, so benzene we have taken here, RCOCl stands for acid chloride, right? In presence of anhydrous aluminium chloride, what is going to happen here? So in here, the acyl group is going to get attached to the benzene. Which is the acyl part? This is COR or else RC double bond O. So this is your acyl group. Okay, so what is going to happen? This is going to attach to the benzene. You're going to get COR here. So what is it again? It is a ketone, right? This is an alkyl aryl ketone. That means you have an aryl group, you have an alkyl group and a ketone here. So this is again ketone. Clear? So now example, when benzene is treated with acetyl chloride in the presence of anhydrous aluminium chloride, it gives acetophenone. So benzene we have taken, CH3COCl we have taken. It is acetyl chloride obtained from acetic acid. Okay, so acetyl chloride, what is going to happen? This is your acyl group part, that is COCH3 is going to attach to the benzene and you are getting a ketone here. So on one side you have a phenyl group, another side you have a methyl group. So this is a ketone. Which ketone is it? Acetophenone, because it is obtained from acetic acid. Clear? So now moving on to the physical properties of aldehydes and ketones. Methanol is a gas at room temperature. Ethanol is a volatile liquid. And other aldehydes and ketones are liquid or solid at room temperature. So that means the lower aldehydes and ketones are gases in nature. That means containing 1 to 2 carbon atoms, and the medium ones or the middle ones, that is containing 2 to 14 carbon atoms, those will be liquids, and the higher ones, as it is having more and more carbon atoms, they will be solid at room temperature. Boiling points of aldehydes and ketones are higher than those of the hydrocarbons and ethers of comparable molecular mass. Okay. Now, the reason is weak molecular association in aldehydes and ketones arising out of the dipole-dipole interaction. So, in aldehydes and ketones, there will be dipole-dipole interactions because of the polarity of the carbon-oxygen bond. So, because of that, the dipole-dipole interactions in aldehydes and ketones, they will be having more boiling point compared to the corresponding hydrocarbons and ethers. Boiling points of aldehydes and ketones are lower than those of alcohols of similar molecular mass because of the absence of intermolecular hydrogen bonding. So, if you are comparing intermolecular hydrogen bonding and dipole-dipole interaction, intermolecular hydrogen bonding is the stronger one. So, because of that, alcohols, okay. So, alcohols will be of course having the highest boiling point because it is having intermolecular hydrogen bonding. Then comes what? Aldehydes and ketones, okay. Aldehydes and ketones, because of the dipole-dipole interactions present, and then you have hydrocarbons. Okay, then you have hydrocarbons. So, this will be the order. So, aldehydes and ketones will be having lesser boiling point than of alcohols because they do not have intermolecular hydrogen bonding. Now, the lower members of aldehydes and ketones are miscible with water in all proportions. So, they form hydrogen bonds with water. So, aldehydes and ketones have the possibility to form hydrogen bonds with water. So, it is soluble in water, but only the lower ones, that is containing 1 to 2 carbon atoms. More than that, they won't be soluble with water. Clear? So, you have taken the first ketone, that is acetone is taken here, CH3CO CH3. So, of course, this bond is polar. So, oxygen will have a partial negative charge, and this is H2O, which is a water molecule, and the hydrogen will have a partial positive charge. So, there will be a bond which is formed between the oxygen of the ketone and hydrogen of the water molecule. So, this is an intermolecular hydrogen bond which is formed here. Right. The solubility of aldehydes and ketones decreases rapidly on increasing the length of the alkyl chain. That means more and more alkyl group is there, means it is going to be having more hydrophobic part, hence the solubility will decrease. Aldehydes and ketones are fairly soluble in organic solvents such as ether and methanol. Even though they are not much soluble in water, they are soluble in organic solvents like ether, benzene, etc. Lower aldehydes have sharp pungent odors. They have pungent odors which is very disturbing. As the size of aldehydes increases, the odor becomes less pungent and more fragrant. Okay. So, lower aldehydes and ketones will be having pungent smell and the higher ones will be having a good fragrance. Clear? Now, moving on to the chemical properties of aldehydes and ketones. So, first we are going to study nucleophilic addition reaction. So, we are going to add a nucleophile here. Okay. So, what is nucleophile again? Which is having attraction towards positively charged species. So, it itself will be negatively charged, right? So, the nucleophile Nu minus we have mentioned here because it is a negatively charged species, attacks the carbonyl group perpendicular to the plane of sp2 hybridized orbital of carbonyl carbon. In the process, hybridization of carbon changes from sp2 to sp3. So, let us understand this. So, this is your carbonyl carbon which is mentioned here. So, to the carbon, two other groups are being attached. So, if it is an aldehyde, one is going to be an alkyl group and another one is going to be hydrogen. If it is a ketone, both are going to be alkyl groups or aryl groups. So, because of the electronegativity difference between carbon and oxygen, oxygen will attract the shared pair of electrons towards itself and oxygen will have a partial negative charge. Carbon will have a partial positive charge. So, we are studying nucleophilic addition reaction. So, a nucleophile is going to get attached here. So, where will the nucleophile attack? Because it is having a negative charge. Nucleophile is negatively charged species. So, carbon is having a partial positive charge here. So, the nucleophile is going to attach to the carbon. So, nucleophile will attack the carbonyl carbon, right? So, it is going to attack here. So, in this case, okay, in this condition before the attack, the carbonyl carbon is sp2 hybridized, right? You have 1, 2, 3. 3 further atoms attached to it. So, it is sp2 hybridized in this condition. So, now once the nucleophile is attached here, what is the structure you are getting? You have your A and B and the oxygen also, that is this oxygen which is partially negatively charged, and the nucleophile is also present above the plane. So, now you can see what is the hybridization. It has become sp3. So, it is a tetrahedral structure that you are going to get. Okay, all 4 bonds are there. So, it is tetrahedral. Okay, it undergoes protonation, that is H plus is going to be added to the O minus and you will get the OH here. So, this is how the nucleophilic addition will take place, that is from sp2 to sp3 hybridization it will move. A tetrahedral alkoxide is formed as intermediate which captures the proton and gives the electrically neutral product. Clear? Now, moving on to the reactivity, ketones are less reactive than aldehyde. due to steric and electronic effect. So this is important. Comparing aldehydes and ketones, ketones are less reactive due to these two factors. So the first one is steric effect. The presence of two bulky substituents in ketones hinders the approach of nucleophile to carbonyl carbon than in aldehydes having only one substituent. So comparing aldehydes and ketones, aldehydes is RCOH, that is RCHO, and ketones you have RCOR dash. So comparing aldehyde and ketone, in aldehyde you have only one alkyl group or aryl group. But in case of ketone, on both sides you have an alkyl or aryl group. Okay. So because of this bulky groups compared to hydrogen, of course the alkyl groups are heavier, right? So because of the presence of only one bulkier group here, the reactivity of aldehydes is more, because it is easy for the nucleophile to attach or attack this carbonyl carbon, because only one bulky group is here. But coming on to ketone, on either side we are having two bulkier groups. So what happens? It becomes difficult for the nucleophile to attack the carbonyl carbon. I hope it is clear, right? Because of the reasons, that is called as steric effect. That means more and more bulkier group is present. It becomes difficult for the nucleophile to attack the carbon. The next reason is electronic effect. The electrophilicity of the carbonyl carbon in ketones decreases due to the presence of two alkyl groups. Hence, aldehydes are more reactive than ketones. So, alkyl groups are electron donating groups. So, what happens? It is donating the electrons. So, what happens is the electrophilicity or the electrophilic nature of the carbonyl carbon will become less. So, in here, in case of aldehydes, you have only one alkyl group. So, it is not much of an issue. So, but compared to ketones, what is going to happen? Both are alkyl or aryl groups. Hence, the electrophilicity of the carbonyl carbon will become much lesser. Because of that, the nucleophilic reactivity of the ketones will be lesser than the aldehydes. Now, first reaction we are going to study, that is addition of hydrogen cyanide HCN to aldehydes and ketones. So in the first step, CN minus, so in HCN, which is the nucleophile, CN minus is the nucleophile, right? So it attacks to the carbon of the carbonyl group to form alkoxide ion. In the second step, protonation of the alkoxide oxygen creates the cyanohydrin product. So what is going to happen? HCN is going to produce CN minus and H2O, right? So this CN minus is your nucleophile. So to the carbonyl carbon, CN minus is going to attach. So carbonyl carbon is this one. Again, as it is polar in nature, oxygen will be having partial negative charge, carbon will have the partial positive charge. So CN minus is nucleophilic, it is going to attach to the carbon. So what is that? You are going to get already these two bonds are there and the CN minus will get attached to the carbon. So what will be here? This double bond will break, of course. O minus will be left here. So that O minus is shown here, to which we are going to add proton. Protonation takes place. It is going to attach to this oxygen and you will get cyanohydrin. This is called as cyanohydrin, where you have the CN and the H will be added here. You will get the OH. So this is called as cyanohydrin. I hope it is clear. So let's take an example of a ketone, which is acetone, CH3 COCH3, to which we are adding HCN. HCN, the nucleophile is CN minus. So what is going to happen here? CN is going to attach to the carbon and the intermediate you are going to get is CH3, CCH3, and you have the O minus and the CN is going to attach the carbon. Now to this, it undergoes protonation. H plus will be added to the O minus. You will get CH3, CCH3, OH and CN. So this is called as cyanohydrin. So this is called as cyanohydrin. The next one is addition of sodium hydrogen sulfate. Sodium hydrogen sulfate is NaHSO3. So in NaHSO3, the nucleophile is HSO3 minus and Na plus is positively charged. So HSO3 minus is going to get added here to the carbonyl carbon. So saturated solution of NaHSO3 in water when mixed with aldehydes or lower members of ketones forms crystalline bisulfite addition product. So as discussed, in carbonyl carbon, oxygen will get the partial negative charge, carbon will have the partial positive charge. So this HSO3 minus part is going to attack the carbon and Na plus will attack the oxygen because it is negatively charged. So what is going to happen? ONA you are going to get, right? O minus will be there, Na plus will be there. So it is OSO2H, which is actually SO3H itself. So it is forming a bond with the oxygen. That is why it is written like this. So that will get attached here. That is, this HSO3 part is going to attach to the carbon and sodium is going to attach the oxygen, which is shown here. Now again, proton transfer will take place. That means proton transfer. That means H plus transfer is taking place. This hydrogen, that is the H plus ion, will be coming here and the sodium will go here. So what you are going to get? OSO2Na and OH is going to be obtained here. So this is the bisulfite addition product. So first what will happen? NaHCO3, the HSO3 part will get attached to the carbon, Na to the O. Then what happens? Proton transfer will take place. Hydrogen will come here, sodium will go there. So that is a product you are going to get. Okay. Now the next one is, so now let's take a specific example here. CH3, CHO and NaHSO3 we are going to add. So here what happens? HSO3 minus is going to attack the carbon. Na is going to attack the oxygen because it is partially negative charge. Now what is the product you are getting? CH3COSO2H, that is the HSO3 minus part, and ONA. Now proton transfer will take place, hydrogen will come here, sodium will go there. So you will have OSO2Na there and OH here. Clear? So that is the product which is formed. Now the next one is addition of alcohols. Aldehydes reacts with alcohols in the presence of dry HCl gas to form acetals. Okay, so what you are going to get? Acetals. When aldehyde or ketone reacts with alcohols, you get acetals. Acetals are geminal alkoxy alkanes in which two alkoxy groups are present on the terminal carbon atom. In this reaction, the addition of one molecule of alcohol to one molecule of aldehyde result in the formation of hemiacetal. So first what is going to happen is, to the aldehyde or ketone, we are going to add one molecule of alcohol which forms a product which is called as hemiacetal. To the hemiacetal, we are going to add again one more molecule of alcohol wherein we'll get acetal. So let's see the reaction. This is your aldehyde to which ROH, what it is? Alcohol is going to be added. So here also OH minus, R and OH minus will be there. OH minus is the negatively part, that is the nucleophile which is going to get attached to the carbon, and the alkyl part will go and attack the oxygen. So you have RCOR, OR dash will be attached here and the OH part will be attached to the carbon, and this hydrogen was already there which is shown here. So this is called as hemiacetal. So to this we are going to add one more molecule of alcohol. So what happens here? The alkyl part is going to attach this H, and what happens? The H2O will be removed. So you have OH here and the H is removed from here, which will form the H2O. The alkyl group is going to attach here and you're going to get RCOR dash OR dash, and this hydrogen was already there and you'll get water. This is called as acetal. Clear? So let's take an example of the reaction of methanol with ethanol produces the following result. Okay, so acetaldehyde we have taken CH3CH2 and CH3OH, which is methyl alcohol. So oxygen is having a partial negative charge, carbon will have a partial positive charge. So what is going to happen? The nucleophile OH minus is going to attack the carbon atom and the alkyl group will be attached to the oxygen. So you get CH3COH and OCH3. So this is going to attach here, you get the OCH3, hydrogen is already there. So this is hemiacetal, to which again we are going to add one more molecule of methanol. So what is going to happen? One more molecule if you are adding, that alkyl group will be attached to the hydrogen. Hydrogen will be replaced and in place of that the alkyl group will come. So you have the OCH3 there also, already one OCH3 was there. So this is your acetal which is being formed. Clear? Now the next one is, ketones do not readily react with monohydric alcohols. However, they combine with diols to give ketols. Okay. So aldehydes can react with monohydric, that means which contains only one alcohol group. It can react with them and form acetals. But ketones do not readily react with monohydric alcohols, but it can react with dihydric alcohols. That means two hydroxyl group containing alcohols, and it will form ketones. Okay, so let's see. This is ketone here, RCOR. It reacts with ethylene glycol. That is a dihydric alcohol. So what is going to happen here? This bond is going to break, and what is that you are going to get? So this OCH2 and OCH2 is going to get attached to the carbon atom, and this O and these two hydrogen, that is this hydrogen and this oxygen will form water. So what is going to happen? This bond is going to break, and you are going to get two new bonds with the OCH2. So that is shown here. So you'll have RCR, OCH2 and OCH2. This is ethylene glycol. Ketal will be formed and water will be removed. So I hope how ketal and acetal is formed is clear to you. So ketal will be formed using a dihydric alcohol. Clear? So in the next session, we are going to see the chemical properties of aldehydes and ketones. Further reactions we are going to see. So I hope the concepts that I've covered in this session is clear for you. So that's all for today. Thank you.